I've had several questions about this problem, so I thought let me work it out on a video, and maybe if I explain where I think some of the hard parts might be, perhaps that'll help you guys get through this one a little bit better, or even just get a deeper understanding of what's really going on, even if you've already solved it. So first, let's just look at the problem. Let's see what are we really being asked for here. So find dw dy, and then we have x in this subscript outside the parentheses. And what this means is that we're going to treat x as an independent variable, just like we treat y as an independent variable. Okay, and so find dw dy with x as an independent variable, and we want to evaluate it at a given point, and then we're given two equations. So first we're given an equation for w, and so w equals 2x squared y squared plus 2yz minus 2z cubed. And then we have this other sort of constraint equation here, which is x squared plus y squared plus z squared has to equal 6. So in a sense, this is an equation for a sphere, so you can think of this as the points that are going to go into the equation for w are going to come from the surface of this sphere. In other words, x, y, and z are constrained to be on that sphere. Okay, so maybe just kind of thinking of it that way a little bit. Okay, now we are trying to find this derivative over here. We want to know what that derivative is. And we're going to take a bit of a roundabout approach to try and find it, but one of the things when the math gets detailed and tedious is that it's always important to remember what is it that you're looking for. So find dw dy with x treated as an independent variable. So the first thing we're going to do is we're going to take this equation here for w, and we're going to differentiate it. Okay, so on the left hand side, I've got dw dy. Keeping in mind I'm going to treat x as independent, so what do we have to do here? Well, okay, let's go to the first term. The first term is 2x squared, right? Y squared, and we're going to differentiate that with respect to y. And since x is independent, we are just going to treat x as a constant. So the derivative, so what you want to think of here is that when we do, if we take this whole equation, this guy, and we are just multiplying the equation, we're multiplying the equation by dy, that's where the dw dy comes from on the left hand side, and then so it's multiplying through by dy through all these terms, right? So we're taking the derivative of each of these terms on the right hand side with respect to y. Okay, so for our first one, the 2 is a constant, the x we treat as a constant, so we take the derivative of y squared right here, and the derivative of y squared is 2y. So we have 2x squared times 2y, and that gives us 4x squared y, and that's our first term. Now, you might be thinking, well, wait a minute, what's the purpose of this derivative? And just bear with me and I'll come back and talk about that. But let's just get through the derivative. I want to make sure that you understand how to find all these derivatives. Okay, so that's the first term. Now we'll move on to our second term. Our second term up here is 2yz. Now, 2yz, we want to differentiate 2yz with respect to y, but z is one of our dependent variables, so we want to treat z as if it's a function of y. Okay, so if I have this situation here where I have y, which is a function of y, and z, which is a function of y, and I want to take the derivative, I have to use the product rule. Okay, so I'm just going to apply the product rule to this second term. Okay, and in doing that, I will end up with 2z and it's 2z So I'm doing the product rule. Remember the product rule, you take the derivative of the first times the second plus the derivative of the second times the first, right? So I'm leaving the 2z alone, and now I need to take the derivative of y with respect to y, and the derivative of y with respect to y is 1. So my first term is 2z. Okay, so then I'm going to have another term, and in this term I'm going to leave the 2y alone. So this is the derivative of z with respect to y times all of this, so I just get dz by dy. Okay, let me make sure you understand all that. So let's just write the product rule. Here's how I did that. Suppose we have two functions. Let's just call them a and b, and then the derivative, let's just pretend we're doing it with respect to time here, of a, b. If a and b are both functions of time, well, this is equal to dA dt b plus dB dt a, right? The derivative of the first times the second plus the derivative of the second times the first. That's what I did here, and that's where this dz dy comes from. Okay. Now I'll move on to the third term. The third term up here is minus 2z cubed. Now, I want to take the derivative of minus 2z cubed with respect to y, but remember that we're treating z as a function of y. Okay, so let me write out what that turns out to be, and then we'll talk about y. So it's going to come out to be, it's the minus sign just coming straight down from the original equation. It's going to be minus 6z squared dz by dy. Okay, now that completes the differentiation of this. Let's just talk about why that happens. So to do that, I'm just going to start another page here. We'll come back. Oh, I hope I didn't lose that page. We will come back to that page. I will find it. And I want to just work through a little example. So to understand why that happens, suppose we have a function z is equal to y squared plus y. And suppose I want to take the derivative with respect to y, d by dy of z squared. Okay, so there's two ways I can do this. One way I can do it is I can just say, well, let's come over here and do it one way. I've got z squared is equal to y squared plus y times y squared plus y, and if I do this multiplication, I get y to the fourth plus, let's see, I'm going to get a y cubed term here and a y cubed term here, so it's going to be 2y cubed, and I'm going to get a y squared term. And then I can just differentiate this with respect to y, right? So that would give me, just taking normal derivatives here. So that would give me 4y cubed plus 6y squared plus 2y. Okay. Now the problem is that I can't do it this way in our example that we're working on, because I don't know this. All I know is z is a function of y, but I don't know exactly what function of y it is at this point. So the question is, how else can I do this? How else can I compute this ddy of this z squared? Okay, so here's what I can do. It's going to equal 2z, okay, and that's just taking the derivative of z in its entirety, but then z is a function of y, so I need to multiply this by dz by dy. Okay, so what I want to do is I'm just going to substitute in here, and I will show you that that this actually works out. Okay, so first, let me just compute dz dy, right? So that's just the derivative of this, and that's going to be 2y plus 1. So that's this term, okay, which in our problem, I don't really know what that is. It's just going to stay dz dy. But in this problem, I'm showing you what it is so that we can understand better. Okay, so I've got 2z, so this is going to be 2 times z, but z is y squared plus y. I'm multiplying that by 2y plus 1. Okay, so let me just rewrite this as 2y squared plus 2y times 2y plus 1, and now you can see that when I multiply these first two terms together, I'm going to get 4y cubed, and then I'm going to get, let's see, 4y squared here, and plus 2y squared there is going to give me 6y squared, and then my final term is going to be 2y times 1 is 2y, and it comes out the same way each time. So the point here is, if I need to do something like this, d by dy of z squared, where z is a function of y, first I take the derivative of z, which is 2z in this case, the derivative of the whole z term, right? So it's z squared, so the derivative is 2z, and then I multiply it by dc dy. Okay, let's see if I can find where, okay, here's where we were. All right, so now we should understand where all these terms come from. Okay, this one, again, comes from the fact that we are just differentiating this term, and since x is independent, we treat this whole thing as constant. This one is an application of the product rule, and this one, I guess, technically is an application of the product rule too, but just a little bit different, showing you what I did on the other page. Okay, so now I finished that first step. The next step is I want to differentiate this expression here. I would differentiate this one with respect to y too, right? I'm differentiating everything with respect to y. Okay, so now I'm going to say d by dy of x squared plus y squared plus z squared equals d by dy of the right-hand side, which is just 6. Okay, now what we have to remember is some of these terms are treated as constants, some of these terms are treated as dependent variables. X, again, is independent, so we treat it as a constant. So the derivative of a constant is that's just going to go, it's going to become x squared times the derivative of 1. The derivative of 1 is 0, so that term is going to go away. Derivative of a constant. The next term is y squared. So the derivative of y squared with respect to y, well, that's just going to be 2y. Just taking the derivative. Now the next term is z squared. Remember, z is a function of y. So when I take this derivative, this is just like what we did before. I take the derivative first, so I get 2z, but then I have to multiply it by the derivative of z with respect to y. And then on the right-hand side, the derivative with respect to y of 6 is just 0. Okay, so now I have two equations. Okay, I've got this equation here, and I have this equation here, and you can see where they came from, okay, and you can see where all the terms of them came from. I think I've explained every term, where each term comes from, and these are two equations in two unknowns, but the unknowns happen to be derivatives, right? So I have one unknown here is dw dy, okay, and the other unknown is dz dy, which appears here, here, and here. Okay. So let's take this equation. This is a pretty simple equation to deal with, and let's just solve it for dz dy. I want an expression for dz dy. So I will solve this equation for dz by dy. So I move the 2y over to the right hand side and it becomes negative, and then I divide by 2z. Okay, and when I divide by 2z, this goes away. On the right hand side I have negative 2y over I have negative 2y over 2z, which is just negative y over z. So when I solve this, I get dz by dy is equal to minus y over z. Okay. Now that I have this expression for dz by dy, I'm going to substitute this expression into this equation everywhere where I have dz dy, which is just going to be these two places. Okay, so I'm substituting. I'm taking this guy and I'm going to put it here, and I'm going to put it here. I'm substituting back into the other equation, and when I do that, I'm going to try and write this over here. Then I get dw by dz. Now there's a little bit of simplification that takes place here, but basically my first term doesn't change, so it's 4x squared y. The next term doesn't change, 2z. Then I have, so I've got 2y times negative y over z. So that's going to give me negative 2y squared over z. Negative 2y squared over z. And here I've got 6z squared times negative y over z. So the z's cancel, and I get plus 6, well, the z squared, and it cancels with the z in the denominator, and I get a z in the numerator, so it's 6zy, or let's write 6yz. Okay, and now I have an expression for dw dz. I'm sorry, dw dy. This should be a y. Okay, so let's recap where we are right now. We start out, we want to find dw dy with x being treated as an independent. We want to evaluate it at a point. I still haven't done that part yet, but that's the easy part. I'm giving these two equations, so I differentiate both of them with respect to y, dw dy, and I differentiate these three terms up here to get these three terms. We saw that. I differentiate the second equation with respect to y. When I do that, I get a dz dy term. Okay, and so I solve the equation for that dz dy term, and I plug it in up here. Okay, think about it for a second. When I differentiated this equation the first time up here, I got an answer for dw dy, right? And I'm asked for dw dy. But what's the problem? Well, the problem is I've got it in terms of these dz dy's, and I don't know what they are. Okay, and in a sense, that's a product of this constraint here. And so, because what's happening here is we're saying, look, we're not going to just allow x, y, and z to be whatever they want. They can only come from the surface of this sphere. Okay, so if that's the case, then, and we want to understand something about how this w function is changing with respect to y, then there's still 2 degrees of freedom there, right? We can say, well, how is it changing with respect to y if x is independent, or how is it changing with respect to y if z is independent, right? Which way around that sphere am I moving? So that's what that's why this constraint, that's why this additional thing comes in. That's where these dz dy terms come from. And in order to get those dz dy terms, how is z changing with respect to y? That's why I differentiate this equation. That term falls out, and I'm able to solve for it. And then when I plug it back in, I still have dw dy, which remember is what I'm looking for, but now I have it without any of those other derivative terms in there. Another way to think about it is, if I wanted to know how this function w that we're given up here changes with respect to y, if I ask you that question and you think about it, you would have to say, well, it depends. How is z changing with respect to y, right? And that's where these terms matter, right? And what we're saying is, if we keep x, if we treat x, if we're treating x as an independent variable, then we can specify how z is changing with respect to y. And so again, so just kind of a few different ways to explain what's happening here and different ways to look at it to hopefully help you understand it. So to finish the problem, we just plug we plug these values in, right? So we have our expression for dw dy, and we just evaluate it by substituting the x, y, and z values in, and there you go. That solves the problem.